Good afternoon, everyone. I'm Shuchun from the University of British Columbia. So today I'm going to talk about customizing prefetching policies in Linux. Nowadays, data centers become more and more popular. Large-scale and memory-intensive applications are now running in those data centers. However, due to Moore's law, scaling power DRAM has been slowing down. As prior research shown, the cost of DRAM can reach up to 30% of total cost of data center. And because of the high demand of memory, DRAM becomes the main infrastructure expense and thus a performance bottleneck for running memory-intensive applications. We all know when application runs, it generates data temporarily stored in a DRAM. Eventually, if the application cannot fit as a whole into the DRAM, is push the data into some external storage such as SSD or HDD. We all know accessing to DRAM is much faster than accessing to those disks. Under the context of memory management, prefetching is one of the effective ways to reduce such latency caused by the remote requests to disks. Our project is done under one of the widely used operating system, which is Linux. So let's look at what Linux default prefetcher does first. Linux default prefetcher is a sequential prefetcher. Assume this is your memory, you have a faulted page in the middle. Linux not only brings in the faulted page, but also prefetch some pages that physically allocated around this faulted page, because they believe that those pages will be useful very soon. Now we know that default Linux prefetcher is a sequential prefetcher. So it is efficient for sequential memory access patterns such as this. However, there are a lot more other memory access patterns, and default Linux may not be effective to detect those patterns. For example, there is strat access pattern, ladder access pattern, for example. So our motivation comes from an experiment we did. So we implement 3 different benchmarks that follow 3 different memory access patterns. And also, we also implement 3 corresponding memory access pattern prefetcher as well. For each benchmarks, we see their corresponding prefetcher performs the best. And there's no single prefetcher outperform all others for all the benchmarks. So we believe for different applications that follow different memory access patterns can benefit from its corresponding prefetching policy, and there's no one-fits-all policy exists. So our goal is, in order to improve individual applications' performance, we want to be able to enable customization of application-specific prefetching policies easily and efficiently in Linux kernel. People may just implement policies inside the Linux kernel directly, but it's kind of hard because mechanism and policies are already entangled in a giant Linux code base. First, it requires a huge engineering effort to understand and implement policies in Linux kernel. Secondly, because Linux kernel code is frequently being updated, it's kind of hard to maintain your policies with frequent changes. So our solution, we propose to leverage eBPF to allow easy and efficient kernel prefetching policy extension. So in this case, user can write their own prefetching policies without actually need to modify the kernel source code. Our system, which is called FetchBPF, simplifies this development process of prefetching policy in Linux kernel, and we show negligible performance overhead using our framework. There's some prior research have shown that using eBPF for easy policy customization, for example, prior work called SIRP, exposes kernel information to define scheduling matching policies across kernel, networking, and application layers. There's also work called P2Cache, which allows customized configurations for page cache, eviction, prefetching, and swapping policies. For P2Cache, it only allows a user to turn certain configurations or parameters of prefetching policies, and the baseline prefetching policy does not change. For our frameworks, we provide more flexibility. We allow users to design their entire policies. Before we talk about design of our framework, let's talk about how prefetching works in Linux. When application runs, page file generates, and then it traps into operating system. The first thing operating system check is that if the faulted page actually presented a cache or not. If the page is actually in the cache, then we are lucky. We just need to update a statistic for prefetching algorithm that Linux kernel keep track of, and then map the page into the page table. If we don't find that in the cache, then we have to do prefetching, and this is where the prefetching logic will be executed. The prefetching policy will determine number of pages to prefetch, and also which pages to prefetch. At the end, it calls the kernel mechanism to actually fetch the pages based on the swap entry offset inside of the swap cache. So our design follows this prefetching workflow. So this is the page fault handling path we just talked about. We place 2 hooks on this page fault handling path. The first hook, which is hook A, is placed when page fault happens. At this hook point, user can attach their program to collect faulty addresses. They can analyze this history of faulty addresses to find applications' memory access patterns. And the second hook, which is hook B, is where prefetching policy are taking place. Programs attached at this hook will contain user-defined prefetching policy, and the default kernel policy will be replaced. What user need to do is that once we have placed those hooks in the kernel, user just need to write their own eBPF program with policies and load them in the kernel. When those hooks are triggered, attached program will be executed. As eBPF program are not allowed to call arbitrary kernel function directly, we wrap up necessary kernel mechanism as eBPF helper functions, so user can call those functions to fetch pages directly in their eBPF program. Here we show one simple policy example of using our frameworks. This is a policy that fetches the faulted page with 2 subsequent physical pages. First is calls our helper function to start Linux block optimization plug. Then it uses the while loop to fetch the faulted page and the following 2. Lastly, it turns off the block optimization plug. Now let's look at evaluation. We implement several policies using our frameworks. Except Linux default swap entry offset-based sequential prefetcher, Linux also introduced a virtual memory-based sequential prefetcher called VMA. We implement this using our framework. Moreover, we also implement a state-of-the-art strat prefetcher called Leap with both swap entry offset and page table entry-based versions. Lastly, we have a ladder pattern prefetcher with both versions as well. We want to answer 2 research questions. The first one, we want to investigate if implementing those policies using our framework affects their prefetching effectiveness, such as accuracy or coverage. Secondly, we would like to know if there's performance overhead introduced by our framework. Now, we show some results for our micro benchmarks. We have 6 different micro benchmarks, and I would like to explain what they do first. So the benchmark names always consist of 2 words. The first word specifies the allocation pattern of a benchmark. There are 2 different allocation patterns, sequential and random. For sequential allocation pattern, it means pages in virtual address space and physical address space are allocated in the same order. For random allocation, it means that sequential pages in virtual address space points to the page in physical address space in random order. The second word in the benchmark name refers to access patterns. There are 3 access patterns, sequential, strat, and ladder, that we showed previously. So there's a lot of results for micro benchmark. Let's focus on one example of them. So for this random strat benchmark, we've already explained it's allocates pages sequentially in virtual address space, but randomly in physical address space. After the allocation, it accesses pages in strat pattern. For this benchmark, the policy in red performs the best. Those are actually the same policy, but one implement inside of a kernel, and another one implemented using eBPF. This policy is actually a page table entry-based VMA policy, so it won't be affected by the random order allocation in physical address space. Moreover, since it can detect strat access pattern, it performs the best for this random strap benchmark, and this is what we expect. Due to the limited time, please check out our paper for more evaluation details. In the paper, we also have evaluation results for accuracy and coverage of prefetching policies we implemented. We also have evaluation results for macro benchmarks. For all the evaluation results, policies written in our framework shows equivalent performance as just natively implementing them in the kernel. Thank you for your time, and I'm happy to take questions.